Okay, so hello everyone. I'm really excited to be here with you on the first edition of the NDC AI conference. I heard that many of you had 2 intense days of the workshops already, and also the amazing keynote today of Jody. But I had an impression that we're talking quite a lot as the whole industry only about LLMs. And in this talk, I decided to take a look from a little bit different perspective and to talk about the concept that is more general for all of the machine learning solutions. But we are going to touch a little bit on LLMs as well at the end. So today we are focusing on something called continual learning. So the ability of the machine learning models to learn continuously. And I would like to present it to you on a real-life use case from the medical field that I had the pleasure to work on. But first, I would like to introduce myself. My name is Agata Chudzińska, and as my name suggests, I'm Polish. But over the last years, I have been working for a Hamburg-based German company, which is AI consulting company. So we're implementing different projects for various industries. And I have been doing that for like almost 10 years now, so working with different kind of projects. But what would be more interesting for this part, so me and my team over the last years have also worked quite a lot in the medical field, so helping medtech companies build their products. But to make it a little bit more clear, what do I mean by that? So we're mainly working with the medical images, so such as CTs or MRIs, to detect different structures, such as the bones or here the liver. So the bones are a little bit easier, but it shows here an example that these are 3-dimensional structures. With the liver, it's more complicated because you have all of the tiny veins in there, which are super crucial when you're doing liver resection. So if you cut in the wrong place, it can have very serious consequences for the patients. So we are also suggesting the right place to cut the liver. And all of that may need to build it for our partners to be used in the extended reality solutions, so to help the surgeons to plan the surgeries and do the measurements on the real organs, and as well as to do the teaching of the next doctors, but as well the patient education. But today I've chosen one of our most challenging projects in this area, which is called Focal Cortical Dysplasias. It sounds a little bit mystery, but we're going to explore it together a little bit more. But before we do that, I would like to draw attention to statistic that was quite shocking to me before I started working on this project, which is that around 50 million people globally have epilepsy, or according to different statistics, around 1% of the global population, which is making it one of the most common neurological diseases globally. And as you can imagine, this is quite heavily impacting the life of the patients. But if this wouldn't be enough, every epilepsy patient is supposed to have 24 higher risk of dying unexpectedly because of a phenomenon called sudden unexpected death in epilepsy patients, called SUDEP. So we can all agree this is quite serious, and it would be good to dive a little bit deeper in this area. So if you want to do that, sooner or later, we'll exactly see our focal cortical dysplasias, and a little bit spoiler, things which look like that. So what are those FCDs? If we take a magnifying glass, we'll see something like that. So these are the misbuildings of the human brain, which are very frequent cause of epilepsies, specifically those epilepsies that are pharmacoresistant, meaning quite many patients can just take drugs and live a normal life, but unfortunately there is also quite a big group which can't, so they have the pharmacoresistant form of epilepsies. The good news here is that the FCDs are potentially operable, but the most important here is to find them. So how do they look on MRIs? So just a very short recap, if you're lucky enough to never have MRI in your life, so just a very short introduction. So MRI stands for magnetic resonance imaging, so it's basically being done by MRI scanner, which you can see like here. So this is like a big tube making strange loud noises. You go inside it and it uses electromagnets and radio frequencies to make very detailed pictures of our inner body without cutting or whatever. And using different settings, you can expose a little bit different features. So we are going to talk about it very briefly later on. So knowing what MRIs are, let's explore how do FCDs look like on them. So there are a few different specifics. They can come in different variations, so they can be 2, 3 of them in different combinations, but these are the most common features that help us recognize them. So first of all, it's blurry boundary between the gray and white matter, which you can see on the first picture, right here. There can be also thickening of the cortex, the unusual duration or the unusual folding of the human brain, hyperintensities, which is also quite important, as well as transmantle sign. This is another very specific feature, which you can see on the second picture right here, which is like a visible path towards the brain ventricle or towards just the brain center here. But not to make it too easy, they can differ in size, they can be present in many different areas of the brain, and they can also have very different shapes. But when things go well, and usually epileptologists or also neurologists find an FCD, like the big one right here, the patient can undergo brain surgery. So this is a real one, not AI-generated picture, and the patient can become seizure-free. So, having all of that knowledge, I have a small task for you. So if you already know all of the features about how do FCDs look like, a few seconds for you to tell me if any of these patients has an FCD. Any ideas? You can just tell the number 1, 2, or 3. Number 2. Number 1, number 3. All of you are right. That was a tricky question. But as usually in situations, FCDs are not so clearly visible like in the books or like in the examples that I've showed you before. The reality is much more complicated and it's really hard to find them. I mean, ourselves, when we worked quite a lot on the technical side on this project, we're not able to recognize it on the level like the doctors do. So, as we all have seen, this task usually requires really experienced epileptologists, and as with all very niche experts, there are not so many of them. So our idea was, how about using AI for that? I mean, if you think about it, so what is machine learning for? For detecting subtle patterns in the data, and to also make the access to it more democratized so that non-experts can also use the model to recognize specific features. Sounds like a perfect hit, right? So we decided to start a research project. So the experts from our team joined forces with the biggest epilepsy center in Germany, in Hamburg. And we have also taken the real Dr. House, Dr. Patrick House, to lead our project to make our odds even better. We did a machine learning project, so let's talk about our data set, because the data is the most important part here. We managed to that point to collect the biggest at this time data set of FCDs, which consisted of 201 MRI series. One thing I didn't mention earlier, MRIs are not a single picture, this is a series of pictures. So in our case, it was 192 pictures in one series, and they are all analyzed, so these are three-dimensional data. But we didn't want to recognize FCDs knowing that there are some. We wanted to discriminate and to recognize which of the patient has it and which not. So that's why we also added 100 normal MRIs. And as life is not perfect, there can be also different pathologies in the brain. So we didn't want our model to react to any abnormality in the data, so we also have given it like brain tumors and different pathologies as well. I talked about the settings. So in our case, we use the T1 and FLAIR sequences. So these are the types of the MRIs, which T1 is focusing mainly on the shapes. T2s, which we didn't use, is focusing on the fluids. And FLAIR is like a specific type of T2, which is exposing more the abnormalities. And we also included the suboptimal quality MRIs because the patients are moving, there are some artifacts happening. We just wanted it to be as close to reality as possible. And we spent really a lot of time, I mean, the medical experts, on making sure that this FCD is really an FCD. So doing double visual analysis, using the EEG, so the electrodes that you can have on the brain, and as well as analyzing the types of the seizures that the patients were having. You can think why 200 is like biggest to date data set, like it's not a lot when you think about machine learning. Well, one of the things is that you really need the niche experts, and the annotation process is really not easy. I mean, as you have all seen, it's not easy to spot an FCD, but to even say where exactly does it start and what does it end is even more tricky. So it has taken really a lot of time. Even though we tried to do it semi-automatically, it still required really a lot of time of the experts. So yeah, we have our data, so let's train the neural network right now. Not so easy. As I said, 200 examples, 200 series is not a lot, and for such a complicated problem, it didn't work. But I would have lied if I said we didn't try. Of course we did, but it just didn't work. So we have taken a step back, and we have worked with the pre-processing of the data. And we did that in 3 steps. So first of all, we did the brain tissue segmentation. This is actually quite a solved problem. You can easily achieve like 97% of accuracy with the existing neural networks, so we will not focus on that too much. But we did that for 2 reasons. First of all, we wanted to exclude the data that are not relevant. So all of the skull and different things, we just removed it. It's not important here. But more importantly, we did that as a prerequisite to the second step, which is the morphometric analysis. So it turns out that the epileptologists over the years, they also created their own methods to exposing a little bit some of the features in the data. So one of them is the method developed by Huppert's, which we were inspired on by developing the pre-processing in our case. So we used here the junction and extension images. So for the junction, it relies on the masks of the gray and white matter. That's why we had to do the first step. And it's making mathematical calculations, basically standard deviation and mean, on the intensities so that we can expose a little bit better the intensity feature that we know it's quite important for recognizing FCDs. The second one, extension, it's quite an interesting thing. I also, not long time ago, was in a cybersecurity talk, and they also said that similar method is being used to detecting any changes in the images. So the idea here is that if we add more blurring to something that was already blurry, it's exposing it even more. So also on the example of the images, it helps you detecting which parts of the image has been changed. So here it's allowing us to detect more the blurring feature of the FCDs. And then we just created our final input. So we did padding, cropping, standard operations, and created 4 channels as input to our model. So now we can go to the neural network part. We have really played a lot with many different architectures, but I will just show you the one that we finally used here. Some of you recognize this is the UNet architecture. It's not super new one, but surprisingly doing very well for the medical segmentation the whole time. Just a very short recap of how does it work. So the UNet architecture is a variation of the encoder-decoder architectures. So in the first part is the first part of the U that we have. It's the encoder. So it's basically compressing the information. So from big image that we have with limited number of channels, which are 4, we're just making it smaller and smaller and creating abstract features. So we have at the end here in the bottleneck, like quite small images, but with quite many features, which are encoding specific features like some type of lines and edges and stuff like that. And in the decoder part, from this bottleneck, we are trying to recreate either the original image or we are trying to recreate the mask. Like in our case, this is quite huge FCD present in here. And the idea here is that if we try to compress the data in this bottleneck, we are collecting all of the most important features for our target to be recognized. We did also additional feature here, so this is a variation of the decoder. It's not influencing the results here, it's just helping us to not overfit the whole model. Just a short note, by the way, so even though we are having all of the newer architectures like transformer-based and etc., surprisingly still on many benchmark, the UNet-based architecture is still doing very well. I think right now by small margin, the combination of UNet together with transformers is actually leading in quite many benchmarks. So let's take a look at our metrics and results. So we compared the traditional object-wise metrics, so on the level of the whole series, did we recognize the FCD, yes or not? And the voxel-wise, so voxel is like pixel, but in 3D. So we're just taking a look at each of them and saying, was it right or was it wrong? And we get actually quite nice results. So we recognize 70% of the FCDs that were there. Precision at the level 54, it's not bad. So our model was sometimes creating false positives, but it wasn't really that bad. The dice is quite low, but it's very hard to say where does FCD finish. Like, is it still part of the FCD or not anymore? So that's why it's a little bit lower. And as we're working in a medical field, you always need to do a clinical validation if you want to move your project further. So we did that. Sorry for a little bit complicated table, but I will guide you through it. So let's take a look at the columns first. In the middle, we have our ground truth, meaning it was checked by many different things, so we know that there were 9 FCDs in there. On the left-hand side, we had the result of neuroradiologists, so the doctors specialize in analyzing the brains, but not specifically in epilepsy. And on the right, we had our neural network. So if we compare the true positives, so we see that there were 9. The doctors were able to recognize 3. Our model was able to recognize 7, which is quite cool. But then we also have taken a look at the different things that we can see here, which is that we had the specificity of 5.5%, meaning that our model was very frequently saying that there is an FCD, even there wasn't. So I wanted to understand what happened. And I really encourage you, every time you work on machine learning projects, really try to understand why did the model behave in this way. So we have found out that in the majority of the cases of the false positives, the model was recognizing 2 or 3 FCDs, which in reality is theoretically possible, but it doesn't happen that often. And if it's just said there is 1 FCD in there, it was in the majority of the cases true. So why did it happen? It turned out that our model reacted quite a lot to the artifacts. So if someone moved a little bit, there was like some additional noise in the data, it was detecting it as an FCD. There were also similarly looking lesions. So as I mentioned to you, not every of these features that we mentioned earlier is a sign of FCD. So for example, detected blurring, which is one of the signs, but actually in this case, the doctors said it wasn't. It was just blurring, not FCD. And we also seen that we had an uneven location of the FCDs. So in the majority of the cases, the FCDs present in our training data set, they are in specific part of the brain. So the model was overreacting and suggesting that in this part of the brain, there are the FCDs. And what we have seen as a result is that we had different data distribution than the reality. So actually in our case, we had like half of the cases were having FCDs, whereas in the majority in the real life, they are just single patients, not half of the population having it. So we're left here with some of the challenges. We have quite many false positives, which is making the tool actually a little bit useful for the initial screening, but still giving you too many false positives, it's like lowering your attention level. We have data collected only in one hospital, so the variance is quite low for the different scanners. Very obvious, but medical data are very sensitive, and this is going to be important for our next part. And when developing medical solutions, we have to be in line with all of the medical certification regulations. Right now, also with AI Act, it's getting even more complicated. So with that, we have been thinking, okay, so what to do next? And we decided to dive a little bit deeper into something called continual learning. But before we do that, let's just recap very quickly, how do we usually work on machine learning projects? In a simplified way, of course. So we start with understanding the problem. Then we collect our data set. We do many different experiments of the different architectures. Then we finally have the version that we're happy with, and we deploy it in production, and we live happily ever after. That's good that there is some laughs in there, because, of course, the life doesn't work that way, not in machine learning. So sooner or later, we'll have, for sure, data drift. So the distribution of our data will change. Be it, for example, using different scanners in our use case, or maybe the behavior of our clients will change. Or the fraudsters will change their behavior because our financial system models will recognize the fraud, so they'll start to behave differently. Maybe we'll want to add new classes. So I told you that we are having also different kind of pathologies in the brain. So how about we, apart from FCDs, we would like to also recognize brain tumors, if we already have a model that does it quite well. Maybe we want to add a new task. So if we have a model that is very good at summarizing text, why not classifying it? No matter how long we collect the data set, there will be bias in our data. So all of that will decrease the performance of our model in time. So what we can do against it? So let's analyze a few strategies. So first of them, probably that can come up to the mind, is transfer learning. So let's analyze in a toy example, or maybe more specific in a pet example. So let's assume that you have a cat and a dog, and you would like to more frequently take a look on your phone and just to see pictures of your cat or a dog. So you train a neural network, you label just some examples, and you have quite decent classifier. But then a moment of weakness comes, and you buy a guinea pig. And right now you have a problem because you would like to also see the pictures of a guinea pig automatically, but you cannot do it with your existing model, and it knows nothing about it. So the initial idea would be that if we have a model that's recognizing your pets, so it knows the concepts of like, how does an animal look like? It's 4 legs, it's fluffy, or whatever. Let's add just a few examples of a guinea pig, label them, and train our classifier. Will it work? Yes. 99%, great success. But what will happen is that the performance on the original task will decrease. This is a little bit exaggerated. Probably the difference will not be on this specific example that big, but something like that will happen. Why? Because of something called catastrophic forgetting. And if we would like to show it in a little bit fancy manner on a graph, we can show it like this. So let's analyze our situation here. So we are training here our model sequentially, meaning that we start here with the orange line. We train our cats and dog classifier. It's getting really great results in here. Meanwhile, it doesn't know anything about the guinea pigs. But then we take the same model and we train it sequentially next on the next task, like with the guinea pigs, and we have very decent guinea pig classifier, but the performance of the original task is decreasing. And this is the most substantial problem here when we are dealing with sequential training, and this is the most important area that continual learning is trying to fight against. So let's come back to our example and what else we can do. So let's say we can train the model from scratch, right? We just trained the first classifier, so we still have the pictures of our cats, dogs. We just give there the pictures of our guinea pig, train the model from scratch, and achieve great results. And does it solve the task? Yes. I mean, this is basically the best solution what we can do in here, in this, our toy pet example. But if we think about our original example from medical fields, there are some issues that we would have here. So first of all, it would mean that we need to keep the data the whole time there, which is raising the privacy concerns. That's why I said this obvious things that medical data is sensitive. We just can't do that in this way. Apart from that, there can be significant costs when it comes to computation and storage. Maybe for the pets not, maybe for the FCDs not. But if we think about large models, this is really a significant feature. And it's also connected with the carbon footprint, connected with the GPU training, as well as the time that we need, for example, for the months-long training, just to update our model by the new knowledge. So this is where continual learning comes into play, sometimes called as well incremental learning. So the main idea here is that the model should be able to learn incrementally, meaning that they should be able to adapt to the ever-changing conditions, but without forgetting what they learned before. Moreover, they should be able to reuse what they already learned, not to learn from scratch the new skills, but to do it based on what they already know about the world, like we humans do. And this is not a coincidence that the majority of the continual learning methods, they're actually inspired by biology and how the human brain works. And also being considered that continual learning actually is one of the key aspects of intelligence. Like if you want to develop intelligent system, this is something that we really should be taking care about. So again, if you would like to be a little bit more fancy and show it on the graph, we can show it like this. So we can compare the stateless retraining. So each time, assuming there is more data coming in time, we are just training the model either on the whole data set or just like sliding windows, but using the whole data. But we would like to do more in the stateful training, meaning that we have one model and then adapt it only by the subset of the data. So we have three main methods that we can use in continual learning. First of them is the regularization-based methods. So the idea here is that we can penalize the model in the moment when it will want to change the weights of the neural networks that are critical for the previous tasks. And there is quite interesting comparison here towards like how the brain works in such situations. There was an experiment that the scientists did on mice, in which they saw that when mice were learning some new skills, there were new synapses being created. So the neurons were being connected, and when the skill was learned, this connection was getting less and less elastic. So the brain was trying to protect it from interacting with the different neurons. And when this connection was being destroyed, the skill disappeared. So the similar concept here is based for the regularization-based method. So it means, in the technical terms, that when we're training the neural networks, we are recognizing which of the parameters were important for the previous task, and we are trying to protect them by adding additional regularization in our loss function. And just answering a question that might appear, there are methods to do that, for example, via Fisher information matrix, that we see which of the parameters were important for the previous tasks. Of course, it has some drawbacks. So first of all, it doesn't like eliminate fully the forgetting. It's also like not allowing us to use all of the weights fully in the neural network, and it works better for tasks that are very much similar. But the rule of thumb is that we usually should start with this method and then go to the next ones if this one doesn't work. The next area are the replay or memory-based methods. So the idea here is that to recall the model that, hey, you still have the previous task that you should remember, be good at, we can keep some of the data in memory so that the model can still revisit them later. And the biology inspiration here is the role of sleep. So when we are sleeping, our brain is still it's still processing the data that we got to know during the day. And it's consolidating some of the memories so that we are creating our memories and skills. So that's why also the children are also dreaming a lot more, because they are learning more throughout the day. But I bet you also have quite a good sleep after the conference as well. What's the issue here? So first of all, memory buffer size. So we cannot keep all of the data because of the size of our buffer, but more importantly, the data privacy. Because still, if we have the data, we put them in memory, like, are we allowed to do that the whole time? Not really. But what's very common trend right now is to use the generative models. So we can just create synthetic data based on the data that we would like to put into the memory, and then it works very well. So it's being used quite frequently now. The rest part of methods are the architecture-based approaches. So the idea here is that we adapt the architecture when we're adding the new tasks. So either by adding new layers or just adding in new neurons. An example of that is the dynamic network expansion. So when the task increases, we're just adding it in a specific part of the networks. So example for that could be that when we are giving a new task, we're, for example, giving additional attention heads to that. The inspiration here is connected with the neurogenesis process, where the brain, especially in hippocampus, is creating new neurons in the area when we're learning new tasks, so that it still helps against forgetting what we already know. But what's the drawback of this is usually that we should know the boundaries of our task, which quite often is not the case. Usually we want the model to also do many different tasks, and we don't know exactly where the border should be, which is also quite common, especially in the era of the LLMs, that we want to do many different things. So having that knowledge, let's revisit and summarize all of our acts that we have seen before. So let's start again with the data set. So knowing what we already knew about the distribution, we have taken the lesson here and we adapted it to mimic better the real life. So this time the FCDs were only 10% of our data set. So here we had the 30 FCD MRIs, we added 150 normal MRIs as well as 120 other pathologies, and we divided them into 3 data sets. Each of them consisting of 100, so 10 plus 50 is 40. And just to compare to the continual learning part here, so as we are dealing with the different data distribution, maybe some of you could argue that it would be a new task, because right now we're rather going towards the discrimination. So we want to focus not only where exactly the FCD is, but more about is there FCD or not. We decided to go with the regularization-based approach, specifically with the elastic weight consolidation. And it turned out quite well, so you'll see in a minute the results. So we didn't go with the next method. So let's analyze the training strategy that we did. So phase 0 is what we have already seen. So we have the baseline data set, we trained neural network, we got a baseline model, and validated it against our data set. So in the phase 1, we take the first 100 MRIs, and in the first step, we just evaluate it against our initial model and save the results. Then we have 2 training strategies. First of them will be just to take all of the data and train the model from scratch. So we have all of the data that we have so far, so the baseline data set, the data set number 1, we train the model, we give it a fancy name because we published a scientific paper about that, but for this presentation we can call it just all data model. And the second strategy that we had was the continual learning strategy. So we have taken just data set number 1, so just this 100 MRIs that we had, and we trained further the baseline model. Again, fancy name, but let's call it continual learning model. And that's the end of phase 1. In the phase 2, we take the data set number 2, so the next 100 MRIs, and we start again with the comparison. So right now we have 3 models which we can evaluate against. So we do that, we save the results, and then we repeat the same procedure that we have. So here we add new data set, we train all of the data that we had against the model. So that's how we get the all data 2 model. And in the continuously trained model, we just take data set number 2. We use the model that we trained before, so we are continuously training the same model, and we create continual learning 2 model. And in the third step, we can just evaluate the results and save them. So what were the results? The results were actually very promising. So interesting thing that we can see here is that the baseline model behaved as it did before. It was very good at recognizing the FCDs, but it was creating very many false positives the whole time. What happened in the old data? It still kept this, like all of the models actually kept similar performance on recognizing the FCDs. But the main difference is in the false positives. So all data is already quite huge improvement, mainly because we changed the distribution of the data. But what we see in the continual learning approach is that it got even better, like really significantly better results than what we had with training all of the data from scratch. One of the things is that you can see that all data had like recognized in the third round all of the FCDs that were there, so 10 out of 10. This one only 9. But we also analyzed it with the doctors that it's just like one example doesn't make a big difference in such a data set. So it is comparable in this case. Again, we analyzed what happened, how did the model behave. So additional observations. The false positives that appear, they are mainly reactions to the other brain pathologies. So these are the brain tumors and different kind of things. So if we really would like to be more scientifically creating papers. We could just remove them, compare normal MRIs against the FCDs, and then we could say, hey, we achieved 90% of specificity, but that was not our goal. And as the training progressed, we also see that the model wasn't reacting anymore to the specific regions of the brain, which is also quite cool. So concluding that, we have seen that we have the similar level of sensitivity, again, like in all of the models. We have significantly higher specificity in here, but most importantly, for the continually learned model, this version will be more robust for the future distribution changes. It's not so obvious from this data, but if you think about it, if we're dealing with the imbalanced data set, meaning that the positive class is just making a small percentage of the whole data set, if we continue training on all data the whole time, at some point the model would always say there is no FCD in there and be right in 90 whatever kind of cases, right? Because that's the distribution of the data. So that's why the continual learned model, it keeps remembering the most important part from the previous trainings, and it still is trying to keep these weights in there and adapting to the next task, which was this discrimination in our case. So this is going to be much more robust than the previous version. So to sum up this part, this model is already being considered useful for the clinical practice and hopefully to help the neurologist as well to recognize more epilepsy cases so that the patients can get help and go to the experts more quickly. If you'd like to know more, we published 2 papers about that, so you can take a read if you would like to get into the details of the data set or the trainings. If you would have any issues accessing these papers, you can also reach out to me so I can send them to you. But the big question in the room is the connection of continual learning and LLMs. I mean, not only because everyone is talking about LLMs, but I bet some of you already had the thought like the promises of continual learning is actually addressing and being seen quite a lot in how LLMs are working, right? Like if we wouldn't need to retrain the models from scratch each time, the compute time, the costs, it's really huge if we could implement that. So just to be sure, I also see like this year's Y Combinator talk of Andrei Karpathy. Not sure if you know them. This is This is one of the founders of OpenAI. He also worked as the chief AI officer at Tesla for many years. So he claimed that none of the big players is using continual learning right now, which I do believe him, knowing probably his connections there. But why is that? Because it's quite hard. I mean, if we think about how LLMs are being trained, it's not just one training loop, right? We're having different stages. So we have the pre-training, we have the instruction tuning, we have the alignment, and each of the cases can have its own continual learning. So we can pre-train it with the new knowledge. We can pre-train on the new instructions. So maybe if you're playing with parameter efficient fine-tuning or LoRa, so low-rank adaptation, this is a part of the instruction tuning in here. That's also following it. But the tricky part here is that if we try to continuously train all of this, you can have additional problems. So adapting one part can influence the next part. So it's really not so easy, but the field is dynamically evolving and dynamically changing. So one of the examples to that is really from this Friday. And so I didn't manage to read through the very details of this paper. There is also a link if you would like to take a look. But it's very interesting that there is the Google research, they claim to have a new machine learning paradigm for continual learning, which is called nested learning. So the idea here is that instead of having one big learner for the machine learning problems, we actually should create a few smaller optimization loops, which are nested in each other. So the main idea here is that we shouldn't treat the architecture and the optimizers for the training as two separate things, but they should be treated as one and they should be optimized together. They also introduced something called continual memory system. This is also quite interesting because they draw even more comparisons to the human brain. Like the human brain doesn't update at the same speed of everything. It also has something that is happening more quickly and adapting now. And there's also the slower part, which is consolidating the memories that we keep for later. They also propose new deep optimizers. So they also say that the current optimizers like Adam are not so efficient, assuming that you would like to combat the catastrophic forgetting. And they propose a new POC. So this is still quite early research. So for sure it will be interesting to see how this develop. But in their POC, they created the self-modifying architecture. So this is an example, the HOPE architecture, in which it can adapt itself also when it comes to the optimizers, and they are showing quite promising results also in the area of language modeling. So I think the field is really interesting, so there is really a lot of happening. And as mentioned in the beginning, so the possibility to adapt itself, it's really crucial when we want to talk about the intelligent systems. So I think that probably continual learning is going to be one of the things that are going to bring some of the next breakthroughs in AI, be it with LLMs, maybe built with different architectures, but for sure this is going to be very interesting. And with that, thanks a lot. I hope you enjoyed it and you'll enjoy the rest of the conference. If you would like to stay in touch, my details are here, so thanks a lot.